morning all. This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of ECE, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss the arithmetic and logical instructions of 8051 microcontroller. The slides are prepared by referring the textbook, the 8051 microcontroller. Authors are Kenneth J. Ayala and publication is Sengez Learning. The instruction set of 8051 can be broadly classified under the following categories: data transfer instructions, arithmetic and logical instructions, branch instructions, subroutine instructions, and bit manipulation instructions. In this, we are going to study the arithmetic and logical instruction. The arithmetic instructions perform addition, subtraction, multiplication, and division. The arithmetic instructions also include the increment by 1, decrement by 1, and a special instructions called a decimal adjust accumulator. The mnemonics associated with arithmetic instructions are given below: add, ADD, add along with carry, ADDC, SUBB, subtraction with borrow, INC, increment, DEC, decrement, MUL, multiply, DIV, division, DA, decimal adjust, accumulate. The first instruction under arithmetic instruction is add instruction. This instruction is ADD, add accumulator. Add will add the values of operand to the values of accumulator, leaving the result value in the accumulator. The syntax of the instruction is ADD, accumulator, comma, operand. Here, the operand can be an immediate data or a register or memory location. So, this instruction will copy the contents or will add the contents of operand with the accumulator contents, and the result will be get in accumulator. So this we can write the functionality as accumulator content is assigned with the accumulator contents plus the operand. The example, add A comma R naught. Here R naught register contents will be added to accumulator and the result we can see in the accumulator. Add A comma at the rate of R1. So the source data is in memory location whose address is pointing with R1 register. The memory contents will be added with the accumulator and the result will be, you can see, in accumulator. The next instruction is ADDC, add accumulator with carry. ADDC adds the value of operand along with the carry flag with the accumulator, leaving the result in the accumulator. The syntax of the instruction is ADDC, A comma operand. Here, the accumulator contents will be added with the operand contents along with the carry flag, and the result will be placed back in accumulator. Here, the operand can be an immediate data or register or memory location. Few examples are ADDC, A comma hash 56. So hash 56 has immediate data. So the accumulator contents will be added with the 56H and the result will be placed in accumulator. ADDC, A comma R6 along with the carry flag. Here the contents of accumulator will be added with the register R6 along with the carry flag and the result will be stored in accumulator. ADDC, A comma at the rate of R6. So R6 will contain the memory address, some XYZ address. This will be there in R6. So whatever the contents are there, this contents will be added with the accumulator along with carry flag. So the accumulator contents will be added with the memory contents whose address is in R6 along with the carry flag, and the result will be stored in accumulator. ADDC, A comma 30H. Here 30H is the memory. This memory contents 30H will be added with the accumulator along with the carry flag, and the result will be placed in accumulator. The next instruction is SUBB, which is subtract from accumulator with borrow. So borrow will be signified in the carry flag only. SUBB, subtract the value of operand and the carry flag from the value of accumulator, leaving the result in the accumulator. The syntax of the instruction is SUBB A, operand. Here, the operand can be an immediate data or register or memory location. Here, the contents of accumulator subtracted with the operand values minus carry flag, and the result will be stored in accumulator. Few example for SUBB instructions are SUBB A, #56H. Here, the 56H will be subtracted along with the carry flag with the accumulator, and the result we can see in the accumulator. SUBB A, R6. Here, R6 register contents and carry flag are subtracted with accumulator, and the result will be placed in accumulator. SUBB A, @R6. Here, the contents of the memory location whose address is specified in R6 register will be subtracted from the accumulator along with the carry flag, and the result will be stored in accumulator. SUBB A, 30H. Here, 30H refers to the memory location. So, the memory location contents will be subtracted from the accumulator along with the carry flag, and the result we can see in the accumulator. The next instruction is INC, which is increment the operand. INC increments the value of the operand by 1. The syntax of the instruction is INC operand. Here, the operand can be a register or memory location but cannot be an immediate data. So, this instruction will add 1 to the operand 1, and the result will be stored in operand 1. Few example for INC instruction is INC @R5. Here, the memory location whose address is specified in R5 register, that memory location contents will be incremented by 1, and it will be stored in the same memory location. INCA. Here, the contents of accumulator will be added with 1, and the result will be stored in accumulator. INC 30H. So, here 30H is an memory location. The memory location contents will be added with 1, and the result will be stored in the same memory location, that is address 30H. INC R4. The register R4 contents will be incremented by 1, and the result will be stored in R4 register. The next instruction is DEC, which is a decrement the operand. DEC decrements the value of operand by 1. The syntax of the instruction is DEC operand. Here, the operand can be a register or a memory location. Here, the operand contents will be subtracted with 1, and the result will be stored in operand 1. Few example for DEC instruction is DEC @R5. Here, the memory location contents whose address is specified in R5, the contents of the memory will be decremented by 1, and the result will be stored in the same memory location. The next example is DECA, which is accumulator contents will be subtracted with 1, and the result will be stored in accumulator. DEC 30H, which is 30H, here it is a memory location. The contents of the memory location with the address 30H will be decremented by 1, and the result will be stored at the memory location 30H. DEC R4, which is the contents of R4 register will be decremented by 1, and the result will be stored in R4 register. The next instruction is multiply accumulator by register B. Multiplies the unsigned value of the accumulator by the unsigned value of the B register. The least significant byte of the result is placed in accumulator, and the most significant byte is placed in the B register. So here we are multiplying the A register contents with the B register contents. A register content is 8 bits, B register content is 8 bits. The product is a 16-bit size. The 16 bits we are going to be stored in 2 registers. One is in accumulator, the second one is in B register. The accumulator will contain the product, the lower 8 bits, L8, whereas B register will hold the product upper 8 bits. The syntax of the instruction is mul AB. There is no separator between A comma B. We have to write side by side. Mul A by B. This instruction will multiply the contents of accumulator with the B register and the result will be stored in the BA register pair. Lower byte, that is lower 8 bits of the product is stored in accumulator. The upper 8 bits of the product is stored in B register. The next instruction is a div, which is a divide accumulator by B. The div instruction divides the unsigned value of the accumulator by the unsigned value of the B register. Here, the accumulator contains the dividend. The divisor we have to place in B register. After division, the result quotient is placed in the accumulator and the remainder is placed in B register. The syntax of the instruction is div AB. So here the register A will be divided with B. The quotient will be moved into accumulator. After division, whatever the remainder is there, that remainder will be moved into B register. The next instruction is DA, which stands for decimal adjust accumulator. DA instruction adjust the contents of the accumulator to the corresponding BCD number after addition instruction. The DA instruction will convert the hexadecimal value into packed BCD. The syntax of the instruction is DAA. The accumulator contents after addition, then only we are going to be execute DAA instruction. So when the DAA instruction is executed, before executing DA instruction, whatever the accumulator contents are there, this will be checked for the lower 4 bits. That is, accumulator contains bit 0 to bit 3. If it is greater than 9 or auxiliary carry is equivalent to 1, then the 6 will be added to the accumulator. After adding the 6, again we are going to be check the upper 4 bits or carry flag is equivalent to 1. The upper 4 bits will be checked whether it is greater than 9 or not. If it is greater than 9 or carry flag is equivalent to 1, then the accumulator contents will be added with 60H. So which it is going to be result the packed BCD of the result which is exist in the accumulator. The next category is logical instructions. The first logical instruction is ANL, which is bitwise AND. ANL instruction does a bitwise AND operation between operand 1 and operand 2, leaving the result value in operand 1. The syntax of the instruction is ANL operand 1 comma operand 2. Here the operand 2 can be a register or immediate data or memory location, whereas the operand 1 can be a register or memory location. Few example for ANL instruction is ANL A comma hash 12. So here the contents of accumulator will be ANDed bit by bit with a 12H and the result we can see in the accumulator. The second example is ANL A comma at the rate of R0. Here the contents of accumulator will be ANDed bit by bit with the contents of the memory location whose address is specified in R0 register, and the result after AND operation we can see in the accumulator register. The next example is ANL A comma 34H. So this instruction will do the logical AND operation between the accumulator and the memory location contents whose address is 34H, and the result we can see in accumulator. ANL A comma R5. Here the contents of accumulator will be logically ANDed bit by bit with the R5 register contents, and the result we can see in the accumulator. ANL 34 comma hash 34. So here 34 is a memory location, whereas hash 34 is an immediate data. So the memory location contents whose address is 34H will be logically bit by bit ANDed with the immediate data, that is 34H, and the result we can see in the memory location 34H. The next instruction is ORL instruction, which is bitwise OR operation. ORL does a bitwise OR operation between the operand 1 and operand 2, leaving the result in operand 1. The syntax of the instruction is ORL operand 1, operand 2, where the operand 2 can be an immediate data, or it can be a register or a memory location, whereas the operand 1 can be a register or memory location. Here the contents of operand 1 will be perform the logical OR operation bit by bit with the operand 2, and the result will be left in operand 1. Few examples for ORL instructions are ORL A, hash 12H, so which perform bit by bit logical OR operation with the accumulator contents with the immediate data 12H, and the result we can see in accumulator. ORL A, at the rate of R0, this instruction will perform the logical bit by bit OR operation between the accumulator contents and the memory location contents whose address is in R0 register, and the result we can see in accumulator. ORL A, 34H. Here the contents of the accumulator will perform the logical bit by bit OR operation with the memory location whose address is 34H, and the result we can see in accumulator. ORL A, R5. Here the contents of accumulator will perform the logical OR bit by bit with R5 register, and the result we can see in accumulator. ORL 34, hash 34H. Here the memory location contents whose address is 34H will be logically ORed with the immediate data 34H, and the result we can see in the memory location 34H. The next instruction is XRL, which is bitwise XR operation. The XRL instruction does a bitwise exclusive OR operation between operand 1 and operand 2, leaving the result value in operand 1. The syntax of the instruction is XRL operand 1, operand 2. Here the operand 2 can be an immediate data or register or memory location, whereas operand 1 can be a register or memory location. Here the contents of operand 1 will perform the logical exclusive OR with the contents of operand 2, and the result will be placed in operand 1. Few examples for this instruction is XRL A, hash 12H. Here the contents of accumulator will be exclusively ORed with the 12H immediate data, and the result we can see in accumulator. XRL A, at the rate of R0. Here the contents of accumulator will perform logical exclusive OR with the contents of memory location whose address is specified in R0, and the result we can see in accumulator. The third example is XRL A, 34H. Here the contents of accumulator will perform logically exclusive OR operation with the 34H memory location, and the result we can see in accumulator. XRL A, R5. Here the contents of accumulator will be performed logically exclusive OR with the register contents, that is R5, and the result we can see in accumulator. The last example is XRL 34, hash 34H. Here the memory contents whose address is 34H will perform the exclusive OR operation bit by bit with the immediate data 34H, and the result we can see in the memory location 34H. The next instruction is CLR instruction, which is a clear register or bit. The CLR instruction set to 0 all the bit or bits of the indicated register or bit. If the register is a bit, only the specified bit is affected. The syntax of the instruction is CLR register or bit. Few example is CLR A. So here the contents of accumulator will be cleared after executing this instruction. The next one is CLR 01H. 01H is a single bit memory location. So the contents of that bit in the memory location 01H will be cleared. CLR C, which is clearing the carry flag. The next instruction is set B, which is set bit. The set B instruction set the bit operand of value to 1. The instruction can operate on the carry flag or any directly addressable bit. The syntax of the instruction is set B bit. So this instruction will modify the bit whichever is specified in the instruction. Set B 63H. So this will modify the bit which is there at the memory location 63H. Set B01H, the 01 memory location contents will be set to 1. Set BC, after executing this instruction, the carry flag will become 1. The next one is CPL, which is a complement a register or bit. CPL complements operand, leaving the result in operand. If operand is a single bit, then the state of the bit will be reversed. If the operand is accumulator, then all the bits in the accumulator will be reversed. If the operand is a bit of a output port, the value that will be complemented. The syntax of the instruction is CPL, operand, or bit. Few example is CPL-A. So this instruction CPL-A will clear the contents of accumulator, will complement the values of the accumulator. CPL-B, CPL-C, so which will complement the carry flag. The next instruction is RL instruction, which is rotate accumulator left. This instruction shift the bits of accumulator to the left only by one time. The leftmost significant bit. So when you are shifting the contents of accumulator towards LSB, the B7 bit, that is MSB bit, will be copied into the carry flag. B6 will be moved to MSB position, next B5 like this B0, and the LSB will be loaded with the 0. The syntax of the instruction is RLA. The next instruction is RLC, which stands for rotate accumulator left through carry flag. The RLC instruction shift the bits of accumulator to left through carry. The accumulator contains B7 to B0, which is 8-bit size. The MSB bit will be copied into the carry flag, and B6 will be placed into the MSB position, followed by B5 like this B0, and the LSB will be loaded with the previous carry flag. Before executing this instruction, whatever the carry flag is there, that will be loaded here. For each and every rotate operation, it will perform for only one time. The leftmost significant bit, that is bit 7 of the accumulator, is loaded into the carry flag, and the original carry flag before executing this instruction is loaded into bit 0 of the accumulator. This instruction can be used to quickly multiply a byte by 2. The syntax of the instruction is RLCA. Example also RLCA. The next instruction is RR, which is rotate accumulator right. This instruction shift the bits of the accumulator to the right. So when the accumulator contents are shifting towards the right side, the LSB bit, which is bit 0, will be moved to carry flag. The bit 1 will be moved to LSB position. Previous MSB will be moved to the next adjacent bit, and the 0 will be inserted in the MSB. The rightmost bit, that is bit 0 of the accumulator, is loaded into the same bit 0 will be copied into bit 7 position. The rightmost bit, bit 0, will be copied into the bit 7 as well as into the carry flag. The syntax of the instruction is RRA. Example is RRA. The next instruction is RRC, which is rotate accumulator right through carry. This is accumulator contents from B0 to B7. Before this executing, we have some carry flag. So this instruction will shift the contents, towards right side along with the carry flag. When we are shifting this, the B0 will be updated into the carry flag. B1 will occupy the LSB position. B7 will occupy the next bit adjacent to MSB bit. The previous carry will be placed in the MSB position. The rightmost bit, that is bit 0 of the accumulator, is loaded into the carry flag, and the original carry flag is loaded into bit 7. The syntax of the instruction is RRCA. Example is RRCA. The last instruction under logical instructions is swap, SWAP, swap accumulator nibbles. SWAP, swap the bits of the accumulator, that is the lower nibble, that is bit 0 to bit 3 will be loaded into bit 4 to bit 7. Similarly, bit 4 to bit 7 will be copied into bit 0 to bit 3. So, bit 7 to bit 4 will exchange the data with the bit 3 to bit 0. This instruction is identical to execute the rotate operation without carry either towards left side or right side by 4 bits. The syntax of the instruction is SWAP A. Example is SWAP A. Thank you all. So in this session, we have discussed the arithmetic and logical instructions. Under arithmetical instructions, we have studied the various arithmetic operations like addition, subtraction, multiplication and division, increment, decrement, decimal, adjust, accumulator. Right. The various instructions which we have studied under arithmetic operations is ADD, ADDC, add along with carry, SUBB, subtract with borrow, INC, increment, DEC, decrement, MUL, multiply, DIV, division, and DA, decimal, adjust of the accumulator. Next, we have discussed the logical instructions. The various logical instructions we have discussed is ANL, which is logical and, ORL, logical OR operation, XRL, exclusive OR operation. Next, we have studied a few complement instructions and set instructions, clear instructions, CLR instruction for clear, set B for clear setting the bit, and CPL, which is for complementing the bit or register. Next, after that, we have discussed few shift operations and rotate operations like RL, rotate left, RRL, that is RLC, RCL. These instructions for rotating the carry towards left side. The next we have discussed RR instruction, which is rotate right accumulator, RRC, rotate right accumulator along with the carry flag, and the last instructions we have studied is grab instruction. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.